Welcome back to the Python for Beginners series. This series is intended for beginners who have never encountered the language and want to learn everything from scratch. In this episode, we'll explain working with more complex Python data objects and explore the functions for working with these objects. I will show the examples in the Jupyter environment. I have also prepared several notebooks for the demonstration. I leave it up to you whether you also open Jupyter and try the examples right away, or whether you study only by watching the video. If you are going to try the examples right away, open a terminal and type the Jupyter Notebook command. So, here we go. So far, we've only introduced a few basic Python data objects: numeric objects, string objects, and Boolean objects. However, the enormous power of the Python language is based on the implementation of container data objects. Such objects are lists, tuples, dictionaries, sets, and frozen sets. To make the list absolutely complete, it should be said that Python also uses the binary data types bytes, byte array, and memory view. As the icing on the cake, the last used data object is none. To get familiar with data objects, Python has several categories into which it classifies objects. The first view of objects can be from the point of view of their use, that is, what data or values can be stored in them. That's why we have text, numeric, sequence, map, set, Boolean, and binary types. Special categories are none types, which are simply nothing. In some other languages you may encounter the null type, which is exactly the none type in Python. The second possible view of data objects is from the point of view of their mutability. We divide objects into mutable and immutable. What does it mean? So far we have only encountered unmutable objects. We create such an object, assign it to a variable, and the object has the same value throughout its life, which cannot be changed. If we need to change its value, we have to create a new object and assign it to the same variable. This causes the interpreter to forget about the original object. Conversely, we can create mutable objects, which include some container data objects, and modify them arbitrarily during their lifetime. We can add data to them, remove data, but the object that holds the data will remain. Now we will gradually introduce the individual data objects. By far the most used data objects are lists. Once we understand lists, we will understand working with other data containers. They are all very similar to a certain extent. Lists are mutable data objects that store a sequence of individual elements. This means that together with these elements, they also store information about their order. We can read and use the individual elements of the list at any time, but since the object is mutable, we can also add, remove, or modify them at will. We have already encountered a very similar data object. It was a string data object. It also stores individual letters and, together with them, information about the order. If the string were to forget the order of the individual letters, we would not be able to read the sentences we stored in it. However, unlike a list, the string data type is immutable. Any objects can be inserted into the lists. Most often, numbers or strings are stored in them, but if I said that we can store any objects in them, then these objects can also be functions, classes, modules, or even other lists. But it is very important to realize the basic property of lists. If we insert any element into the list, we do not insert the object as such, but only insert a reference to this element. Therefore, if we insert any mutable object into the list and then change its value in the list will also change. Let's see how lists can be used in practice. A list data object can be created in several possible ways. The easiest is to create an empty list, into which we can then gradually insert individual elements. Having said that a list is a mutable data object, elements can be added and removed in a very simple way. Since every list is an instance of the list class, we can use either simple notation using square brackets or calling the list function to create an empty list. The second way is to create a list by writing an enumeration of its elements. We separate the individual elements with a comma and we can write any Python objects. The third possible way is to use the list function, which we pass any data source as a parameter. In the first case, we will use the range object, which we have already met, and in the second case, we will use the string object as the data source. I said that an element of a list can be any object. Therefore, in the last two examples, we will test this functionality and add the language's basic data object classes to the list, and also test the list containing Python's built-in functions. Let's take a look at the created objects. This is what the lists we created look like. Python displays them in square brackets to make it clear that this is a list object. The first is an empty list, then a list of numbers, and so on. Noteworthy is the list we created from the string object. As you can see, Python split the string into individual characters and added them to the list. The last two lists contain references to object classes and built-in functions. I'll show you the magic with them in a little while. Two arithmetic operators are allowed for list objects. We can add and multiply lists. The meaning of these two operators is the same as for the string object. If we add two lists, a new list object will be created, which will contain the elements of the individual operands and will of course also respect their order. When multiplying lists by integers, as with strings, the list will be repeated as many times as the numeric operand indicates. As with strings, the order of the operands is not important. Of course, abbreviated notation of operators can also be used. We can also generate lists using loops. I'm using a for loop to demonstrate this feature, but we can also use a while loop. In this example, a for loop will run through all the elements of the string object. This means that each letter of the sentence "Hello World" is used in turn and added as an element of list 8. To make writing such a task easier, the Python language introduces the so-called generator notation. Since we want to generate a list object, we enclose the expression in square brackets. So what's going on inside? The right part is the same as the standard for statement. Each time the loop passes, the next element of the string is assigned to the letter variable. But an expression was added before the keyword for. It says which element will be added to the list. Because we want to add the exact letter that appears in the string object, we do not modify it in any way. Therefore, there will be the same expression. But we will perform the calculation in the following example. We have a sequence of numbers in list 2 and we want to create a new list that will contain the squares of those numbers. Therefore, we perform the calculation in the first part of the expression. In another example, we can create pairs of numbers and their squares. The last example looks scary, but it's nothing more than 3 nested for loops. To demonstrate how Python can be effective in writing code, I also provide an example of standard notation. As you can see, the result is exactly the same. The list object implements two methods for bulk modifications. The append and extend methods allow adding additional elements to lists. We showed the append method a while ago. The append method allows you to insert one or more elements into a list. It does not manipulate the elements in any way and inserts them as they are. If we put another number in the number list, nothing unusual happens. But if we insert another list into the list, the next element will be the list object and not its individual values. However, if we wanted to insert individual elements, we would have to go through the entire inserted list and add element by element. For this case, Python introduces the extend method. This one will do all the work for us. For clarity, this is what the standard notation would look like if we use the append method. In order to work with the individual elements of a list, Python allows us to access them using indexes. The principle is the same as for the string object. The first element of the list has an index of 0, and each subsequent element index is always one number larger. Likewise, a negative index is also introduced, which is used to select elements from the end of the list. As with strings, slicing is also simple, allowing you to select a specific section of the list. I promised magic a moment ago. At the beginning of these demos, we defined a list that contained Python's built-in functions. We'll remember it just to be sure. The list contains links to 4 functions. To make it clear that we can still access the individual elements of the list as objects, we will show how to call functions stored in the list using an index. We know that the print function is contained in the list and has an index of 3. Let's call it. Exactly what was supposed to happen happened. The interpreter looked in the list, found a reference to the print function, and executed it. What will happen on the next line? We have shown how to insert list elements using the append and extend methods. But Python also introduces other methods for working with list elements. The append method always inserts a list element at the end. But if we need to insert an element at a precisely specified place in the list, we can use the insert method instead. The insert method inserts a new element before the element with index 2. After insertion, of course, the indexes are shifted. The pop method retrieves the list element with the specified index. At the same time, the element will be removed from the list. If we do not write the function parameter, it is always executed for the last element of the list. The remove method removes an element with the specified value. If such a value is found in the list, it is removed. But if it doesn't exist, the language interpreter throws an error. If we do not enter the function parameter, the first element of the list will always be deleted. Sometimes it can be useful to find out the index of some list element. So that we don't have to go through the entire list and compare the values, Python provides the index method. The index method finds the first occurrence of the specified value in the list. If we try to find the digit 9, the interpreter returns the index of the first occurrence, for in our example. As a second parameter, we can enter the index from which we want to perform the search. Therefore, if we know that the first occurrence of the digit 9 is in the 4th position, we can perform the search from the 5th position and get the result 8. The third optional parameter can be the last index to limit the range. So we can look for the digit 9 between the 2nd and 6th index of the list. If the list element is not found, the interpreter throws an error. Python also offers options to order and sort the list. The reverse method reverses the order of elements from last to first. So it doesn't deal with sorting elements by value. Conversely, the sort method sorts elements by value. If we add an optional reverse parameter, we can get the list in descending order. The last thing I'd like to show is the use of multidimensional lists. As we said before, a list element can be any object, including another list. If we create a list of lists, we call it a multidimensional list. We have already created one like this. Let's show it again. You work with this list in exactly the same way as with other lists. If we want to access individual elements using indexes, we first write the index of the first level and then the index of the second or other levels. The next most used container data object is a tuple. A tuple is basically a list. With one difference. A tuple is an immutable object. But this rule is only partially true. For a tuple to be completely immutable, the objects in it would also have to be immutable. But this rule is not true. As in a list, we can insert any objects into a tuple. The tuple only guarantees that the order and the number of inserted objects will not change. However, if some elements of the tuple are mutable, as in the case of a list, it may happen that their content changes during the execution of the program. We work with tuples in the same way as with lists, but because they are immutable, there are of course missing methods for adding and removing individual elements. Changing the order of elements is also not allowed. Let's look at tuple magic in practice. A tuple data object can also be created in several possible ways. the easiest is to create an empty tuple, but since we said in the beginning that a tuple is an immutable object, we cannot insert new elements into it. Therefore, such a creation is actually pointless. The second option is to create a tuple by writing a list of its elements. We separate the individual elements with a comma and we can write any Python objects. Correctly, we should always enclose tuples in round brackets, but the language interpreter expects that as soon as we write several objects separated by a comma, it is a tuple and will complete the brackets itself. Tuples are great for assigning values to several variables at the same time. What happened? We created a tuple of objects A, B, and C. If the objects didn't exist, the interpreter created them for us. We assigned a tuple of values to this tuple. This means that each element of the tuple on the left received the value from the right, in the same order as they were listed. To make sure of this, we can print them. Creating tuples from data sources works exactly the same as for lists. We can create them from strings, from a range object, or perhaps from a list. We can also add or multiply tuples. In principle, it is the same as for lists, with one difference. Since a tuple object is immutable, such an operation always creates a new object. It is then assigned to the same variable so that we can work with it. If we would like to verify this, we can call the built-in ID function, which will return the unique identifier of the object. As you can see, after manipulating the object, the identifier has changed. One invaluable use of tuples is very easy notation if we need to shift variables. Let's look at an example. If we want to shift the values of 3 variables, we can proceed as follows. We will create a 4th variable that will temporarily store the contents of the first variable. Then we shift the remaining variables and finally assign the value from the temporary variable. At the end, we clean up after ourselves. But Python offers a much cleaner notation. We can call this procedure packing and unpacking tuples. Only one rule applies. The number of variables in the left tuple must match the number of expressions in the right tuple. If this rule is violated, the interpreter throws an error. However, since it may happen that we do not know in advance how many values we will receive, Python allows an exception to this rule. If we write an asterisk in front of one of the variables, we tell the interpreter to assign to this variable all the values that the other variables did not take. Values into such a variable will be wrapped in a list. If there is no value left, the variable will contain an empty list. As with lists, tuple values can be accessed using indexes. But if we try to change the value of any element of the tuple, the interpreter throws an error. Other work with tuples is the same as with lists. Another very frequently used data object is a dictionary. A dictionary is similar to the JSON data format and is used for the same purposes. Unlike the previous types, the dictionary stores pairs of keys and their values. It is optimized to quickly and efficiently find the value when the key is entered. The key can be any immutable object, but most often a string or number is used. There are no restrictions on the value. A dictionary is a mutable data object. As with the list, items can be added or deleted in the dictionaries at will, without the need to create a new data object. However, working with indexes is completely different. Individual items cannot be accessed using numeric indexes, as is the case with lists, for example. If we need to access a value that is stored in a list, the index is the key of the pair. Let's create some dictionaries. The elements of the dictionary are always made up of a pair of data, where the first is called a key, the second a value. They are separated by a colon, and each such element in the dictionary is separated by a comma. On the first 2 lines we create 2 different dictionaries. The first dictionary has string keys, the second dictionary has integer keys. This is standard notation, using an element enumeration. On the third line, we create a dictionary using the dict function. A function can receive any number of named parameters. This means that the key becomes the name of the variable and the value becomes the value of the variable. As you can see, even though the key will be of type string, it is not enclosed in apostrophes. On the fourth line there is an example of creation using the dict function. As parameters, the function is passed a list of lists, each containing two values. The first value will be used to create the key and the second value will become the pair value. The last example of creating a dictionary also uses the dict function, but the parameters are of a different type. The first parameter is a list. It contains key and value pairs. Python even allows you to use another list and tuples in one list. Only one rule applies. A key-value pair must always be passed. The third parameter is given as a named value, that is, the name of the variable and its value. Let's see what we did. We see 5 dictionaries created. Notice the first, third, and fifth. They contain the same keys and values, but each time in a different order. If we ask the interpreter if they are the same, he will answer that they are. Another way we can create a dictionary is the fromKeys method of the dict object. Since this is a method, we need to call it using the dictionary class. The method requires an arbitrary list of dictionary keys. For the demonstration, I show both the call with a tuple parameter and a list parameter. The meaning is the same. The interpreter did not throw an error and created a dictionary skeleton. Skeleton contains keys, but the value of each key is none. The last method we will show is the generator notation of the for loop. We have already used this with lists and tuples. The principle is the same, but be careful that we are creating pairs of data. Key and value. Therefore, the for statement is preceded by two expressions, separated by a colon as required by the dictionary. Working with dictionary items has a lot in common with the previous objects, but also some of its own specifics. If we need to access the individual values of the dictionary, we do not use the index that indicates the order of the element, but we access it by the key value. We can just as well use the get method of the dictionary object. It is necessary to pass the value of the key as a parameter. If the specified key exists in the dictionary, the interpreter returns its value. But as you can see, if we search for a non-existent key, the interpreter does not raise an error, but returns a none object. As the second parameter of the get method, we can specify a default value. This applies if the key is not found. The get method leaves the dictionary unchanged. In contrast, the pop method can pick up a dictionary element and it will be deleted by the interpreter at the same time. The pop method has the same parameters, but its behavior is different. If the key does not exist and a default value is not provided, it will throw an error. We can avoid the error, as in the case of the get method, by specifying a second parameter. This is used when the entered key is not found. The last method we will consider is the pop item. The method does not require entering parameters and always picks up the last item. Dictionaries allow us to work very efficiently if we need to merge or replace a set of elements. The update method adds all non-existent elements to the dictionary and at the same time replaces the existing elements if their value in the source is different. I created 2 dictionaries. There is an intentional error in the second dictionary. Key 3 contains the value 4. As soon as we update the first dictionary with data from the second dictionary, key 3 will be overwritten, as you can see. The remaining keys 4 and 5 are merely added. In some cases, we only need to get a one-dimensional view of the dictionary. This means that we don't need to see the entire data pair, but only the keys or values. Views serve us to look at the dictionary in such a different way. Python offers 3 possible views of dictionary data. All can be used as data generators. The first view returns all key value pairs. As can be seen from the output, the method returns a list of tuples. The other two methods return a list of keys or values of the given dictionary. If I said that view output can be used as generators, at least one example should be given. The for loop in our example takes each entry from the dictionary, creates a tuple object, and then prints it. We can notice that we don't use parentheses when creating a tuple, even though we could. The interpreter of the language inserts them himself. The last data objects we will consider are the set and frozen set objects. A set is an object similar to a list, but with two major differences. The first difference is that the set does not store information about the order of the elements. Its elements are thus unorganized. And the second, even more important difference is that a set guarantees the uniqueness of elements. Each element can be contained in a set only once. If we try to insert an element into the set a second time, the contents of the set will not change. A set is a mutable object, elements can be removed and added at any time. The set is primarily intended to tell us quickly and efficiently whether or not it contains the required element. In order for the set to fulfill this requirement, there is a restriction. The elements of a set can only be immutable objects, typically numbers and strings. Sometimes, however, it might be useful to create a set of sets, in other words, to insert another set as an element of one set. But the set suffers from the limitation of immutability, even though it is itself mutable. Therefore, Python introduces a frozen set data object. This object behaves like a set but is immutable. The creation and manipulation of objects is again best illustrated by examples. Sets have a similar notation to dictionaries. The set is enclosed in curly braces. As in the previous examples, a set can be created by enumerating its elements. But if we wanted to create an empty set, we have to use the set function. By writing empty braces, we create a dictionary type object. A dictionary is used more often in Python, so the interpreter tries to help us and creates a dictionary. As with the other objects we've introduced today, we can create a set object by passing it a data source. If we use an object of type string, the interpreter breaks it down into individual letters and then inserts them into a set. We said that a set can contain any objects, but each one at most once. Therefore, we are not surprised that after inserting the string hello world the set looks like this. Let's see what we can do with sets. We will set up 3 different sets for experiments. The first, important method is union. The union method returns a set object that is created by merging 2 sets. Any data source can be specified as a parameter. I chose a different set for the first example. The method returned a merged set. Again, it is important to note that the contents of the original set are not changed in any way by calling the union method. We can also pass a list to the method as a parameter. The method converts it to a set and performs the required operation. Since it is a logical operation, we can also use the OR operator. The result of the operation are elements that occur in one or the other set. When working with sets, we very often need to find the intersection. We can use the object method, but since this is again a logical operation, we might as well use the AND operator. Intersection returns elements that occur in the first set and in the second set at the same time. The last method we will show is difference. The method returns the elements that are in the original set, excluding the elements that occur in the second set. We can simply say that we subtract the sets from each other. As an example, we will show the long-known generator notation. There is nothing special about it. Since this is a set, it is enclosed in the appropriate braces. Our example will generate a set of all possible squares on the chessboard. Other methods and operators are defined for working with sets. They can be found in the help of the object. I recommend going through the help and trying to work with these methods. So that's all for today's episode. Good job! We explained the work of built-in container data objects that give Python its greatest power. In the next part, we will show how to define custom functions, practice generator functions, and learn how to format output from Python. If you like the Python series for beginners, don't forget to subscribe, and I'd appreciate a like too. I look forward to seeing you in the next episode.